In this lecture, we're going to be taking a look at single-phase half-wave rectifiers with capacitive filters. So up until now, we've looked at how we can implement inductors to improve the output current of a rectifier. But now we're going to take a look at how we can implement capacitors to improve the output voltage of a rectifier. So let's go ahead and draw the circuit for this rectifier. So the circuit is just like the resistive circuit that we looked in the first example, but we've added a capacitor at the output called C1. And so the reason why this helps the output voltage is because capacitors oppose voltage change. And so we can see that by writing the equation of the current through a capacitor, which is given by IC equals C dV dt, where dV dt is the rate of change of voltage with respect to time. So if we solve for dV dt, we get that dV dt is equal to IC over C, where IC is the current through the capacitor and C is the capacitance of the capacitor. So what that means for the circuit is that the larger the capacitor at the output is, the lower the voltage change with respect to time is going to be when the diode is not conducting. So let's go ahead and draw the input voltage and the output voltage and current of this rectifier to see how it works. Okay, so just like before, Vn is going to be a perfect sinusoid, so it's going to look like this, with peak voltage of, let's say, V. But now the output voltage is going to look like this. And I'm going to draw a half-wave rectified sine wave in dashes just to illustrate how the circuit works. So I'm going to put the sine wave like this, going to 0 at pi, and then going up again at 2 pi, and coming back to 0 again. And we're going to define one more point on this output waveform, this point right here where the sine wave of the output changes. We're going to call it omega t1. And then this point right here would be 2 pi plus omega t1. And so the reason why this output voltage looks like this is because from omega t1 until pi over 2, so let's define this point right here, pi over 2, the diode is conducting. So from this point to this point right here, the diode D1 is closed and it's charging capacitor C1. But from pi over 2 until this point right here, 2 pi plus omega t1, the output voltage is greater than the input voltage, so the diode D1 is reverse biased. So let's call this voltage right here VAK1. So we'll say that from omega t1 to pi over 2, D1 is on, and from pi over 2 to 2 pi plus omega t1, diode D1 is off. And again, the reason for that is that the output voltage is being held by the energy stored in capacitor C1. So when the input voltage starts to go negative, so after pi over 2, then the capacitor is holding the output voltage high. And so what that does is that it makes the input voltage lower than the output voltage and reverse biases diode D1. So in other words, VAK becomes negative. And you can see that by the fact that the dashed yellow waveform that I've drawn is smaller after pi over 2 than the output voltage. So then we can say that from omega t1 to pi over 2, so this part of the waveform, the output voltage is going to be of the form Vs sine omega t. Because again, the diode D1 is conducting, so the output voltage is just like the input voltage. However, when the diode stops conducting and the output load is being fed by C1, then the output voltage is going to be proportional to e to the minus t over tau. So this part right here from pi over 2 to 2 pi plus omega t1, where tau is the time constant of the circuit, which is equal to RC. Now, since the output of the circuit is just a resistor, then the output current I out is going to be of the same shape as the output voltage. So it's going to look just like this with peak magnitude. So we're going to say that this point right here is going to be V over R. So again, for a resistor, I equals V over R. And of course, the peak of the output voltage is going to be V. So now let's take a look at our numerical example. So just like in the previous examples, we're going to say that Vn is equal to 170 sine 377t volts. And for this example, we're going to say that R1 is equal to 10 ohms and C1 is equal to 2 millifarads. And so we can compute the time constant of the circuit, tau, which is equal to RC. So it's equal to 10 times 2 times 10 to the minus 3 for milli, which is equal to 0.02. And let's go ahead and draw the output voltage and current. And so we know that a full cycle of a 60 Hz sine wave is 16.6 milliseconds. So we're going to say that this point right here is 16.6 milliseconds. And half a cycle is 8.3 milliseconds. And so a quarter of a cycle is going to be 4.15 milliseconds. And so we know that the output voltage looks like this. It's decaying, then goes up, peaks at 4.15 milliseconds, and then decays after a full cycle, and then starts again. And we're going to say at this point over here, where it starts going up again, is 16.6 milliseconds plus T1. So T1 is the point we've defined as when the capacitor starts charging. So this point right here. And so again, from T1 until a quarter of a cycle, so from T1 to 4.15 milliseconds, so this part right here, the output voltage is equal to 170 sine 377t. But from 4.15 milliseconds until it starts going up again, so until 16.6 milliseconds plus T1, so this whole portion right here, the output voltage is equal to 170 e to the minus t minus 4.15 milliseconds. And so the 170 on this part comes from the fact that the decaying exponential function doesn't start until 4.15 milliseconds. So until this point right here, which is at the peak of 170 volts. And the 4.15 milliseconds inside the parentheses comes from the fact that the decaying exponential function doesn't start until that time. So we need to find the time t1 where the capacitor starts charging. And so to do that, we're going to make use of the fact that we know that at this point right here, at 16.6 milliseconds plus t1, the two functions are equal to each other. So the decaying exponential function, this part right here, is equal to the sine wave function. So this point right here. And so we're going to set the two equations equal to each other at that point, and then we're going to solve for t1. So let's go ahead and do that. So we're going to say that t is equal to 16.6 milliseconds, so 16.6 times 10 to the minus 3 plus t1. And then we're going to substitute that into the two equations and set them equal to each other. So we're going to say that 170 sine 377t, where t is equal to 16.6 times 10 to the minus 3 plus t1, is equal to 170 e to the minus t, where t is 16.6 times 10 to the minus 3 plus t1 minus 4.15 milliseconds. So 4.15 times 10 to the minus 3 over the time constant of the circuit, so 0.02. And so if you solve for this, and obviously you're going to have to use a calculator, but T1 comes out to 1.45 milliseconds. So that would be this time right here. So in other words, every cycle the capacitor discharges for the first 1.45 milliseconds, then charges until a quarter of a cycle, so until 4.15 milliseconds, and then it discharges again until that repeats. Now as far as the output current, then like we said, that's going to be of the same shape as the output voltage. So it's going to look like this. And since it's just a resistive load, it's going to have a peak magnitude of 170 over the resistors of 10 ohms. So this is going to be equal to 17 amps. Now in order to compare this to the previous circuits that we've looked at, let's go ahead and compute the average of the output voltage. And so I'm going to erase this equation at the bottom to make room. And so we're going to say that the average of the output voltage is going to be equal to 1 over the period, so 1 over 16.6 times 10 to the minus 3 times, and now we have to compute two integrals, one from the sine wave and one for the decaying exponential function. And just to make it easy, we're going to compute it from t1 until 16.6 milliseconds plus t1, so full cycle from here until about here. And so the first integral is going to be from t1, so it's going to be from 1.45 times 10 to the minus 3 until 4.15 times 10 to the minus 3 of a sine wave. So it's going to be 170 sine 377t dt. And then the second part is going to be the decaying exponential function. So it's going to be from 4.15 milliseconds until 16.6 plus 1.45 times 10 to the minus 3 of the decaying exponential function. So 170 e to the minus t minus 4.15 milliseconds over tau, so over 0.02 dt. And so if you calculate all this, this comes out to be 0.74 of Vn. So 0.74 of 170, which is approximately 125.64 volts. So we can see here that we've improved the output voltage significantly as compared to the other circuits. So for the example that only had a resistive load, the average of the output voltage was 54 point something volts. So we've improved the output voltage by more than twice by adding this capacitor at the output. And so capacitors are often used for this reason. They greatly improve the output voltage of rectifiers. And so now that we've looked at half-wave rectifier circuits and we've seen how we can use inductors to improve the output current and how we can use capacitors to improve the output voltage, let's take a look at full-wave rectifiers next.